Good morning, everyone. My name is Sienna, and I'm super excited to introduce you all to Beware, our automated honeypot creation and deployment system. So we started this program as like we mentioned, a team of 7 members, 4 undergraduate students from Duke, and 3 students joining us from Riyadh, Saudi Arabia. We all came in with super different levels of cybersecurity experience, but honestly, that's actually what made this work so well. We each brought something different to the table, and we're really able to build something awesome together. When we started this project, our goal was pretty straightforward. We wanted to build honeypots using artificial intelligence. But before I dive any deeper, let's go over what a honeypot is. A honeypot is a fake system designed to attract hackers. Think of it as a trap that appears to be a legitimate and vulnerable server. Just as honey attracts bees, these systems lure attackers away from real infrastructure. And while attackers interact with the honeypot, we're able to learn more about them, their attack, and the intent behind it, as well as prevent actual damage to our networks. So this brings us to the core challenge we identified. In cybersecurity, new vulnerabilities called CVEs, or common vulnerabilities and exposures, are discovered daily. When a CVE is published, attackers often exploit it within hours. However, creating a honeypot to simulate that specific vulnerability typically can take up weeks or even months when created manually by a specialized engineer. This timing gap honestly leaves organizations completely exposed. So then we kind of asked ourselves, what if we could build honeypots automatically when new CVs are discovered, using AI to handle the entire process without waiting for engineers? Here's what our idea kind of looks like. When a new CV gets discovered, our system researches it and automatically builds a honeypot that mimics the vulnerable structure. Then we will deploy it on university servers where it catches attackers trying to exploit the vulnerability. Once we detect malicious activity, the system learns from the attack and blocks the attackers from accessing the real university infrastructure. And so, our focus remained pretty consistent throughout the program. Develop an AI-powered system that automates honeypot creation to protect university servers from exploitation. Sorry. Now, before explaining how we built this system, Halo's going to walk you through the foundational concepts we mastered earlier in the program.
Yes, so going off of Sienna, we knew from the start that our work would basically center around a mix of AI-powered and enabling tools like LLM architecture and RAG for dynamic fine-tuned language modeling, Docker for deploying honeypots, and MCP for integrating external tools with LLMs. And with that, we came up with our first approach. And again, LLMs, large language models like ChatGPT, they use this process called natural language processing to understand and respond to human input. And this is key for us to achieve our goal, as they can therefore interpret user instructions, analyze threat data, and automatically generate working honeypot code. And based on the GPUs allocated to us by the Duke Compute cluster, which was what we used to fine tune, we chose Qwen 3 as a realistic model based on its size and parameters. And we went with this basically to balance performance with cost. And also on the plus side, no user data would have to leave our system, which would guarantee privacy to users. And however, there are some things that we didn't take into account, which Ferris will go into detail about right now.
Hey guys, uh, I'm Faris. Uh, First, fine-tune is basically train a pre-trained model to make it more knowledgeable about a specific area. Our plan was to make it more knowledgeable in honeypot area. So we started by fine-tuning GPT-2, which has 124 million parameter, to improve its understanding of honeypot system using a custom dataset. The result, as you see, were impressive. After fine-tuning, the model provided much more accurate and detailed explanations compared to before. Okay. Going to the next slide, uh, we aim to fine-tune a more powerful model like Qwen 3, which has 8 billion parameters, which support coding and cybersecurity tasks. However, we run into hardware limitation. Even with Duke's high-performance LS40 GPU, the fine-tuning impact was minimal due to the model size. Given these challenges, we shifted to more efficient approach using advanced model like GPT 4.1 through Duke's Light LM proxy. This lets us harness top-tier AI capabilities without the overhead of training large model ourselves. And now my friend Mo will continue.
Instead of that, instead of fine tuning every time, which is time consuming and very expensive process to do, we used a RAG system. So basically, RAG system. So it's like a database. We can keep our updated data there and uh, augment our generation with it as we prompt the model. So we use drag to keep our model updated as our use case is or our like problem lies in a landscape that changes rapidly. So why we didn't use RAG, why we left abandoned RAG, it is because it needs frequent updates. We need to re-index it like every time, like every day or every hour. So it is like very has a lot of complexity overhead. So we choose to use a better and more efficient alternative, which is a direct web search. So instead of using a RAG system, we just make our model, our make access to our web search access to our model. So now going to my colleague David to explain more about.
Yeah, our next approach involved a multi-agent system. And so this multi-agent system was eventually powered by 4.1 or GPT 4.1. But before I go into the specifics of our system, let's go over what kind of AI agents are and what a multi-agent system kind of means. An AI agent is just an LLM such as ChatGPT that can use tools to complete specific tasks. So instead of just having a conversation with it, it might search the web, run code, analyze files, or use any other tools to complete a task. Now, a multi-agent system takes this concept even further. So instead of one agent trying to handle all of the task, we might have multiple agents with their own specialties and their own set of tools, each coordinating with each other to perform a complex task. So for example, we could have a research agent that has access to web searching and web scraping tools. And we could also have a developer agent that has access to coding tools like a code interpreter environment. So the important thing is that all of these agents communicate with each other and work together to complete a task. They build on each other's outputs to enhance their capabilities. So now let's take a look at how our honeypot creation system works specifically. So this is a diagram of our flow. Each of these boxes represents one of the 9 agents that we used. It first starts with our research agent, which researches the vulnerability that we want to replicate by searching the web. That research then flows to our planner agent, which breaks down the implementation of our honeypot into specific and actionable tasks. For each of these tasks, the next 3 agents will work together. So the coder, tester, and reviewer will implement each task and verify its functionality. Upon any test failures, the reviewer and the coder agent will communicate in order to resolve the issue. So afterwards, we have to ensure that our honeypot is working well. And by well, we first mean that we want our honeypot to be really secure. So our security agent over here will perform security checks to see if there are any flaws in the honeypot as a whole. And the reason why this is so important is because skilled attackers might be able to use flaws in a honeypot to use the honeypot as a jumping point into more secure parts of the network. So ensuring this honeypot is secure is a critical step. We'll fix any errors that we see with the code repair agent and then do a final quality assurance assessment to ensure that like our emulation of whatever service or protocol that we're implementing is done well. Finally, our deployment agent over here will write the appropriate Docker files and compose files in order to make it ready for deployment remotely. So with this approach, we were actually able to build our first working honeypot that was deployable and sends logs remotely to blocking services. And since then, we've been able to create a lot more honeypots that implement different protocols. Now, Danny will talk about our front end that kind of tracks honeypot progress.
Thanks, David. So now that our backend was fully functional and able to create honeypots, we needed a front end for our users to interact with. And we used an API to fetch the last month worth of CVEs and populate them onto the dashboard. And this way, the user can initiate the honeypot building process through any recent CVE. And so we integrated our front end and back end using API endpoints. And so here the user selects build honeypot, taking them to a different page showing the last month's worth of CVEs. And they're able to sort the list by CVE type as well as by the recency and severity of the vulnerabilities. And then the user then selects build a honeypot, taking them through the multi-agent pipeline. And then this process is, of course, sped up for purposes of the demo. And then here we can see the user viewing the generated code. And we also have a honeypot library for if a user wants to use a honeypot generated by someone else. And they can add it to their own honeypots, and it will display on their own dashboard. So all beginning from our distant and hazy core idea of making honeypots through AI, we were able to create a finished product automating the honeypot creation process through a complex multi-agent pipeline. And along the journey, we ran into a lot of dead ends, but through this experimental process, we learned a really invaluable amount of information. And yeah, so I'll now pass it off to Ali, where he'll discuss the future of the project.
Technical difficulties for a little while.
Sorry for that. Okay. So for areas to expand and improve, as we look ahead, there are a few key areas we've identified for future development and enhancement. So for code complexity, we aim to better manage and reduce code the complexity of the code. This involves introducing clear abstractions and improving modularity and adding more comprehensive documentation, making the system easier to maintain and extend. So as for smarter LLM support, we are exploring a new how to integrate more intelligent LLM-based assistants, not just for code completion, but for deeper reasoning tasks like architectural recommendations and automated debugging suggestions. And for full CVE history, so security is crucial. We want to support the full life cycle of the common vulnerabilities and exposures, tracking, linking, and prioritizing them across software components. This helps teams act proactively on unknown issues. So as for slides, acknowledgements, we have made this progress. We couldn't have made this progress without incredible support. I'd like to take this moment to recognize and thank some of the key contributors. We have the Duke Code Plus team for their creativity, collaboration, and engineering rigor throughout the project, and also Microsoft team for mentorship tools and strategic guidance. And I would personally would like to thank Duke and all the team, especially Mr. Thomas. Thank you guys for everything you've done for us. I'm talking on behalf of myself and colleagues from Saudi Arabia. This has been a great journey for us. We learned a lot, and we exchanged knowledge in the cybersecurity and AI fields. So we are really grateful. So yeah, that's basically it.